Good morning, everyone. Today is the fourth day of the HOPE meeting. First, we have Dr. BEDNORZ's lecture. Let me introduce the moderator for this session, Dr. Hiraku Ogino from the National Institute of Advanced Industrial Science and Technology. Please welcome Dr. Ogino.
Good morning. Welcome to the lecture of Nobel Laureate. The speaker of this session is Dr. Georg BEDNORZ. He got Nobel Prize in Physics in 1987. He is now IBM Fellow Emeritus. He is a distinguished member of Academy of Ceramics, Fellow of many societies. He got numerous awards, and he got honorary degree of doctor from many universities. It's my very much pleasure to introduce him because he is a hero in our field. His main achievement was discovery of high-temperature superconductivity. Even 70 years after the discovery of superconductivity, the transition temperature remained low. The situation was revolutionary changed after 1986 by the discovery of he and his colleague Alex Miller about the discovery of high-temperature superconductivity in copper oxide. And this was very much epoch-making findings. Please imagine that what had been an insulator was now to be a superconductor even much superior to any metal. It changed not only the field of superconductivity, but also the materials science. And it is natural that the Nobel Prize, his Nobel Prize comes only a year after his discovery. And this is exceptionally short for the Nobel Prize. At that time, I was only an elementary school student, but still I got the news about his discoveries. And this was the reason I subsequently joined the laboratory of high-temperature superconductivity. Okay, today he will give 40 minutes lectures and 15 minutes Q&A. So please join me. Please join to welcome Dr. BEDNORZ.
Thank you, Hiraku, for the nice introduction. Thank you for GSPS to organize such a wonderful meeting. Thank you to all the staff who has been involved for a perfect organization. Today, I'm going to talk about the chronicle of the discovery and the arduous path to the technology of the future. I hope I can convince you that this is the technology for the future to help fight against climate change and all other these problems which we are facing today. When I look at this picture from time to time, I have to reflect my career path. My career path was not at all straightforward. And if I look at this picture, I ask myself, things could have been turned out very differently if I did not have made important and far-reaching decisions and have met with the right people at the right place and at the right time. So 1968 was the release to freedom when I joined the university. And to deal with the freedom is sometimes a hard task. What bring us from school? First, the enthusiasm in science, which had been sparked by my teacher in chemistry. And so I decided to start with the studies in chemistry. So with full expectation, I joined the university, but it didn't take long till I decided that was not the right choice. So the reason was that due to the freedom, I skipped many lessons, many lectures, and I didn't pass important examinations. So I had to start thinking about a different discipline with an interesting curriculum, and my plan B was somehow to start studies of mineralogy with the emphasis on crystallography, which is quite some part of chemistry and physics. So also excursions, geological excursions, turned out to be attractive, not at least because of this girl. She became my wife. So, but during these excursions, I also learned to keep my eyes open to other things. And I learned to read the signs, the hidden signs, when looking at the massive rocks in a stone quarry to find some other jewels. So the fact that I joined the crystallography group in Münster was a lucky event as well, because our professor for crystallography used to work in Zurich at the ETH, and when he came to Münster, he was looking for students who were able to perform a certain task as a summer student, because he was asked by somebody at IBM in Zurich, in Switzerland, whether he would be able to send a talented student to work there in the physics department for quite some while, let's say 3 months. So that was the occasion when I first met Alex Müller. He had joined the laboratory in 1963, already almost 10 years earlier. And what he brought with him was part of his PhD work. That was a class of materials called the perovskites. These are oxides with a very fantastic structure, which is displayed here. The perovskite oxides are building a three-dimensional network of oxygen octahedra, and in the center they are able to incorporate a whole series of transition metal ions. And in addition, in the center of this unit cell, they were able to incorporate alkaline, earth-alkaline, and rare earth elements. So this makes this material a unit class of materials. And one of the materials, like the material he worked on in his PhD work, was strontium titanate, SrTiO3. This became our stone of wisdom. So when I joined the research laboratory as a summer student in 1972, I really discovered that I was entering the scientific gold mine. The rich physics and chemistry of these perovskite oxides are amazing. Materials are changing properties like a chameleon, its color. So we go from an insulator to a semiconductor if we change the chemistry. We go to a metal and a magnet, and even to a superconductor. However, superconductivity existed in these materials, in the strontium titanate, for instance, only at very low temperature, 0.3 degrees Kelvin. But working on these materials, I was fairly soon given the task to to work on crystal growth of perovskites with a fairly complicated machine, but I was very successful. Here I'm proudly demonstrating my first crystal which I grew from the melt. But also I was lucky to be involved, a real member of the physical community in the laboratory. And also I was proud to be socially accepted as a member of this funny brass band which was performing at the IBM family party. So the first day was running quite successfully for me and for my supervisors at the laboratory. And also Alex Müller got alert. He was a department head at that time for the physics group. Now, I repeated this day because I was really enthusiastic about the work in this group. And already at that time, the dream started to become one of my wishes, to once be there a member of the physics group. So in 1974, at my third day, I was performing part of my diploma work in the laboratory, which came to a sudden stop. So after 6 months, I received an official federal decree that I had to leave Switzerland immediately, without having the chance to finish my PhD, my diploma work. So I had to go back to Münster to complete the work which I had done so far as an experimental work. I had just to do some writing. So this appeal was, this request was rejected very drastically. But the physics department head, Alex Müller, had a plan. He invited me for a PhD back to Switzerland. But the plan was not quite easy to fulfill because of these official procedures, which were very difficult. So he transferred my equipment from the IBM research laboratory to the ETH. So my working place became, for the PhD, became the ETH on top of the hill close to Zurich. But still I had some connections, some strong connections to the IBM Zurich lab. And the connections started to evolve when I was presenting these results of my PhD work, the crystals of strontium titanate, which in the upper part, due to the production process, remained oxygen deficient. So this part was a part which is responsible for the superconductivity in strontium titanate, this oxygen deficient part. Some colleague at the IBM lab, Georg BEDNORZ, was interested in superconductivity in some kind of organic compound. He had worked on it during his PhD thesis. And when he joined the Zurich lab, he had the idea, can we do some modification of the carrier density of the reduced strontium titanate? Can we do some niobium doping? So I said, if nature allows so, we will do it and you will get some new crystals. So within 3 days, I was able to take a crystal and send it to Georg BEDNORZ, and he was very enthusiastic about the time between his desire and the wish he got fulfilled. So niobium-doped crystals were superconducting, at higher temperatures. So that was my first encounter with superconductivity. So with niobium doping, the transition temperature could be increased from 0.3 Kelvin to 1.2 Kelvin. That's 300%. So Gerd was very enthusiastic about it and said if we could further increase the carrier density, would it go even higher, approaching room temperature? Well, we tried, but as was be observed later on, also for the cuprates, the increasing in carrier density led to a decrease in the TC and the vanishing of the superconductivity finally. So he lost his interest. I lost the chance to have a new project and continued my PhD, while Gerd, with his senior colleague, Heini Rohrer, started to work on scanning tunneling microscopy. This was a good decision. So they were able to get in touch with atoms and molecules as addressable individuals, and they were able to control and work with an accuracy down to the picometer size. And finally, this brought them the Nobel Prize for Physics in 1986. So I was disappointed to have lost my partner for the superconductivity project, and finished my PhD and got the chance to join the IBM research laboratory in Zurich, or close to Zurich in Rüschlikon. So it was then that Alex Müller took over the flag, because he was just returning from a sabbatical in US, where he had been involved in experiments on superconducting aluminum. So he got interested in superconductivity. And back in Zurich, he began to give lectures about superconductivity at the university. I got the chance to work on a material science project, which got me involved in producing thin films of oxides by different deposition methods. And while doing so, I was slowly driven by the management to combine this film growth process with STM, with a scanning tunneling microscope, as an analytical tool in order to study the first steps of film formation, quasi in situ. This was an ambitious project. And my time as a researcher was not always as relaxed as it's shown here, but I remember this time from these occasions even better than my professional career. So parties were all the time important to get back to real life again, and compensate for a disaster, for instance. But during that time, I really was not satisfied with the result of this research, because the approach came too early at a stage where the scanning tunneling microscope was on its experimental status and was not a real established analytical tool. So this excellent idea proved out to be not too very successful, and I had to consider to change again, even leave the project. But I got the chance to go back to real material science with my own project, and that was a lucky event when Alex Müller came and asked me whether I would team up with him to look for high TC superconductivity in our oxide materials. So he had learned about the Jahn-Teller polaron, and since he was all the time interested in the local properties within these within these perovskite oxides, so he knew what happened if within these octahedra different cations would be replaced, which would show the Jahn-Teller effect. The Jahn-Teller effect means that the octahedra is reacting when, for instance, nickel or copper in the center would adopt a 3 or trivalent state, trivalent or divalent state. So in one case, it could stretch. In the other case, it could contract from the original symmetric way. And if this would be a dynamic effect in a conducting material, it could create polarons. And polarons or lattice vibrations were considered and are still considered as a driving mechanism for the intermetallic superconductors. That was along the BCS theory. So we thought when we would introduce nickel and copper as candidates for such a center in a metallic oxide, we could eventually observe superconductivity. So we embarked on the road towards uncertainty because we didn't have any hint whether this would be realizable or not. Now let me go back and in time and see, because I had to learn about superconductivity, about the topic, and start from the beginning. That was a start into a new area when Kamerlingh-Onnes discovered superconductivity in mercury in 1911. So he observed a sharp drop, a sudden drop around the condensation temperature of helium, namely close to 2.4 Kelvin. Resistance dropped to 0. It's really 0. So mercury showed ideal conductivity below this transition temperature, and the question was immediately, is current transport without loss possible? So, of course, it's possible, but it's not realizable at these low temperatures. So, Kamerlingh-Onnes discovered additional superconductors and said, there are a lot of experiments which we could think about if we use this superconducting state. So he said the consequence of this zero resistance state is the permanent current. Once a superconducting ring is induced with a current by a magnetic field, and the magnetic field is removed, the current would circulate forever. So this would be a permanent magnet as well. So his first approach was to construct a very, very strong magnet, like 10 Tesla. This is more than a million times higher than the strength of the magnetic field of the Earth. But this failed drastically because the coil lost superconducting properties at very small current densities already, and at magnetic fields which were very, very low. So the experiment ended with a disappointment. It was terminated. The breakthrough, however, came only decades later, namely in 1961. So the second criterion to prove superconducting state is the Meissner effect, the effect that a magnetic field which at high temperatures is penetrating the conductor, and below the critical temperature, the magnetic field is expelled. But still, these were not usable properties till the early 60s, when a second type of superconductivity was discovered, named in niobium-3 tin or niobium titanium. So this brought us to superconductors which were able to carry very, very high currents at low temperatures, greater than 10 to the 6 amps per square centimeter. That's 1,000 times higher than we are used to have in copper. And at elevated temperature far away from liquid helium. And they were able to produce very high magnetic fields, but only below this area which is given by these three parameters, below this surface, because as soon as you are approaching Tc, the current density would go down drastically. The same would occur if magnetic fields were applied to these materials. But there were ways around this a dilemma that magnetic field would destroy the superconductivity, because superconductivity in the type 2 superconductors is remaining still when the field is partially penetrating in form of such flux lines, which are normal in the center, but embedded in a superconducting matrix. So the material, despite the fact that a high current is passed and a strong magnetic field is applied to the superconductor, when a magnet is constructed out of them, the superconductivity still survives. So there were a lot of applications emerging with type 2 superconductors. Still, the helium cooling is needed. So superconductivity so far remained a low temperature phenomenon, but turned out to be very useful in magnets used for magnetic resonance imaging, or in devices which were able to detect very small magnetic signals, like in squids. So we knew about high field magnets, which are used now for experiments in plasma physics, in fusion reactors, and solid-state physics. And the biggest superconducting device is a Large Hadron Collider in Geneva, where we have more than 9,000 superconducting magnets, by far the largest superconducting system in operation. So in the first and the largest magnets are shown here in one of the detectors. The first superconducting magnet which failed to show high magnetic fields, and the largest with a dimension of 25 meters are these superconducting coils for a detector in the LHC. So let's start with our research. 3 years later, after our start, there were still no encouraging signs that we would ever end up with a superconducting oxide at a reasonably high temperature. So what we did is we partially replaced ions in the center of the octahedra, sometimes in the center of the unit cell, and the corresponding results in resistivity as a function of temperature. We see here that was our host material, the material we started with, and then did some variations. We were replacing the A site, keeping the nickel site untouched. We were replacing the B site, changing the ratio nickel to copper on the B side. But remarkably enough, the model of the Jahn-Teller effect left us only with 6 different atoms to combine, but still a lot of samples which needed to be investigated. So this was a work which was not very satisfying because there were every day measurements which ended with a disappointment. And this brings me to something which is very true for this activity which we had. It's a quote, or 2 quotes, by St. Georgi, the discovery of vitamin C. He said, the discovery consists of looking at the same thing as everyone else and thinking differently. So, and then he said, a discovery is said to be an accident, and this is even more important, meeting a prepared mind. So having the dream of superconductivity in these oxides, I met a paper which met a prepared mind. So this is a compound which is similar to the perovskite. This is A5B5O15. Here you have a oxygen deficiency. But this research group was looking at this material because they were looking for catalysts. These were a group of chemists looking for catalysts. So this is a pretty boring curve. There's nothing happening between 300 degrees centigrade and minus 100, so they skipped their program on these materials. For us, it was a message: don't touch the center of the octahedra, don't disturb the element in the octahedra. Just keep it stable and constant. So, after 3 years, at this 75th anniversary of the discovery of superconductivity by Kamerlingh Onnes, we came up with a new record temperature in a completely new material. So this was a raise in transition temperature from 23 Kelvin, which was the maximum in the intermetallic compounds, to 35 Kelvin, which is really the transition temperature. Don't worry about the broad transition here, because the samples were ceramic samples and were polycrystalline with a lot of grain boundaries, and it came out later very clearly that grain boundaries can be a big obstacle for the transport of current across. So this sparked a lot of activities in 1987 when our data were published. This is our contribution to the first step in the transition temperatures. And with all the groups which were joining the activities, the temperature was rising very rapidly to more than 135 degrees Kelvin. But the remarkable thing about all of these new compounds is that they are all based on the same building block, the copper oxides, which have been discovered to be essential for the superconductivity. The copper polyhedra are remaining as a main building block, and only the cations on the A side are varied. So this is an example of the series of new materials, 2 groups, bismuth-based compounds, copper oxide, and yttrium or rare earth-based compounds. They are all 2-dimensional structures. They are layered structures, and this is has a consequence for the physical properties because they show strong anisotropy. But let's go to the properties of the high-temperature superconductors as compared to the old ones. We have the high temperature superconductors. They are really designed for a new technology. These are high performance materials, and they are used to substitute copper because of the high electrical current density. So here we have the example, can be more than 200 times higher than the current capability of copper. This is a comparison between the amount of copper wires you need to transport 1,000 amps, and this is the ribbons of a superconducting composite, which has the same capacity. So what high-TC superconducting materials mean for the technology is you have more power in a smaller size. That means it is possible to have a compact design of electrical components, lower energy losses if you think of transporting energy from A to B. You need less resources, and you reduce the carbon footprint by this. Less resources mean also reduced carbon footprint. So it was necessary to transform these superconductors into the form of wires or tapes. And the most advanced technology is made nowadays with the 1-3 yttrium barium copper oxide based coated conductors. What's needed is a support material that's mostly a metallic band. You have vacuum deposition methods which you apply to have multi-layered structures on top of these metallic substrate. And what you would like to have at the end is a flexible material, a flexible composite, in order to be able to make coils and wires. So the reality, however, is more complicated. This is an example from a company producing these composites by different treatments. You have the substrate, you have that's here. You have the protection layer from one side, that's mostly copper. Then you have a lot of buffer layers in between with different deposition methods. And here, the most essential part, it's a superconductor. It's only the order of microns. Here we have 1 micron, but you can design your cables or your tapes with a varying thickness of the superconducting layer. But 1 micron is already is able to have several hundred amps passing through this composite. So the total combination of all these layers is of the order of 0.1 millimeter. So you have still a lot of flexibility in this composite materials. So this makes the high temperature superconducting wires very interesting for application in all areas of a modern energy infrastructure. So we have a superconductivity, which is a key for an environmentally friendly generation, reliable supply, and efficient use of energy. So we have generators already as a prototype to display the power of hydro and wind generators. We have the use in grid technology for the transport, for the distribution, and the protection of the network. And what's also very interesting is the efficient use in form of motors and generators, again, but also industrial processes. And I come to that very quickly. So first of all, the wind turbine generators, they are approaching a dimension which is getting critical, because the volume of the classical wind turbines generators is that high, that big, that you cannot no longer transport it on a public way. So that's a restriction to the dimension. So the generator size, or the power, has apparently some limit. And here we have a comparison between a 8 megawatt a high temperature superconducting generator, permanent magnet were involved to create the magnetic field, and here the conventional superconductor with coils made from copper wires. So what's amazing is the reduction in the use of resources. So from 80 tons copper in the conventional system, you go to 8 tons of copper in the high temperature system. The steel, mostly the support structure, is drastically reduced because of the smaller size of the generator. And the rare earth consumption for the permanent magnet is 2 tons of dysprosium or neodymium, which is a cost factor and a factor of supply. And here it's only 20 kilograms. So one of the first experiments and prototypes which have been installed was in Denmark in 2018. That was the first design and test of the first wind generator. Here we have an example of that. And to compare the dimensions of the classical generator, it's a 3.5 megawatt generator, and the comparison with the superconducting generator. If you compare the 10 megawatt classical generator, which we have as an example from China, it's not easy to transport anywhere. So it probably will stay there in the factory. So we have the transport problem of energy from areas where we have maybe energy production from renewable resources to the places where they are really needed. So we have just a comparison of different systems. What's important here, it's all in the area of gigawatt, and there are really highways passing through the landscape with a lot of room requirement. The right of way here is given with 60 meters, 50 meters in height, which has to be bought from the owners of the land. Here we have a trench width of 25 meters in a 380 kilovolt cable. Here we have the comparison with a superconducting wire system with a really fairly limited trench. The advantage of high DC cables is given here. So you have a narrow separation. You have optimized routing, which is be able to pass populated areas, because the big concern of the public is that they will be disturbed by electromagnetic radiation and from superconducting cables. So where they are constructed, there will be no electromagnetic radiation measurable. So this one brings us to an easier approval by the public and less public resistance. So the latest development is that for the transport of electrical power, it could also be used liquid hydrogen. And in that case, there would be a combination of transport of electrical power and chemical energy when you use liquid hydrogen as a refrigerant. This is an example from installation in New York. Here we have 3 cables, superconducting cables, something like 600 meters in length between 2 substations, for the 3 different phases, transporting something like up to 600 megawatt. And this is a power delivered by a mid-size nuclear power plant, just transmitted by 3 cables. Now, for the distribution, for further distribution in power transmission, there is a paradigm change from the use of high voltage to the use of high currents, which are able to be passed through a superconductor. You have a higher transport capacity at lower voltage. So this is very interesting for retrofit in new urban areas, because you need only fewer cables as compared to the classical ones. The distribution at medium voltage means you avoid expensive high voltage installations and for instance, transformers in city centers. So the critical point is that in such a case, for 1 kilometer cable, which is existing in the inner city of a city in Germany, for 1 kilometer cable you need 70 kilometers of wire. And so the manufacturers of wires are running out of materials. If one would go and have 1,000 kilometers of cable planned for the near future. So here we have the installation of such a cable in the inner part of a city. This big hole in the earth is just only for the joints between 2 cable strands, because the length of a cable strand is limited by the size of the drum which can be transported through the city. So this is a length of 500 meters on one drum, and so in between you have to do the fitting just on the side. That's done here in such a big hole. The rest of the cable channel is only a small trench, and this could be done. This could be installed without any traffic interruption in the inner city of a big inner part of a big city. And interestingly enough, you have 1 cable with a capacity of 5 conventional copper cables. I'm coming to the end soon. One amazing concept has been applied which is used in the metal industry. The metal processing industry is very energy hungry, and one of the processes which is using a lot of energy is to heat such billets, such cylinders of copper or aluminum prior to extrusion, prior to the fabrication of profiles. And this is done with superconducting magnets. This is a conventional heater, uses a lot of energy, goes back goes from the primary coil. Only part of the energy is going to the billet. Here we see this billet being heated up to 600, 700 degrees centigrade, very, very rapid. And here is the magnet heater, which is using which is saving up to 50% of energy. And another advantage is that the productivity is increased because the homogeneity of the heating process, the homogeneity of the heat distribution in the cylinder allows for higher pulling velocity. High current bus bars, usually used in industry to supply currents up to 500 kiloamps, 500,000 amps, are used for zinc electrolysis, for chlorine electrolysis, and also aluminum electrolysis. This is an example of a superconducting bus bar. Here we have the 20 kiloamps conventional connection. Here you have the transition to liquid nitrogen temperature, the cryostat, and here the cryostat is the line for the superconductor, including the cooling system. And if you see the enlargement here, this is a whole tube with a cooling system, the insulator and the liquid nitrogen supply. And this part is a superconducting stack. Here you have again the comparison between the aluminum bars and the superconductor being able to carry the same amount of current. So what's planned at the beginning in the next year is the installation of a 200 kiloamp bus bar based on superconductors in such an aluminum plant, which is a furnace line which can be 1 kilometer in length, up to several hundred furnaces to melt aluminum in a row. The current which is needed is 200 to 400 kiloamps, and you will find the superconducting counterpart to this row of current line on the backside of the installation. Here we have the energy loss, which is over 600 meters, estimated to be 18,000 megawatt hours per year in the case of aluminum, and here in the case of superconducting line, it's only 5%. Something which is may become realizable for everybody here is a project which is running since many, many years in Japan. It's the superconducting train, the maglev, where superconducting magnets attached to the side of the car provide the lifting, the levitating field for high-speed trains. This is an example where high-TC superconducting magnets were once tested with such a vehicle. At present, the plants are still using the niobium-based superconductors and helium cooling, but on the long hand, one can expect that the train between Tokyo and Osaka, which is still in the planning or also in construction partly, will use the high-TC superconductors. So I think in a few years from now, we will at least have the possibility from Tokyo to Nagoya to use the superconducting high-speed train when we would like to go to Kyoto. At present, I was told last year when I was here that somewhere in between here, the line is already under construction, that somewhere in between here in a special prefecture, the governor has some objections for the line to cross his country. So there has to be, I guess, some severe discussions in order to make this project possible. And with that, I would like to close and thank you for your attention.
you very much, Dr. BEDNORZ, for the impressive talk. I believe that audience understands the history of superconductivity and the significance of your findings. So now it's time. Time is open for the questions. So if you have questions, please line up in front of the microphones, and please say your name and institution before the questions. Okay, please.
Thank you for lecture. My name is Ryuichi Nishiori from Nagasaki University. So I feel the structure of perovskite is beautiful. So my question is, symmetry of metal oxide is one of the important factors to realize high temperature superconductivity.
You mean the symmetry of the?
Of metal oxide. So metal center and oxide. So the structure.
I think it seems to be necessary that these materials are layered structures. The symmetry, you see, if you have different compounds, some have pyramids as a building block, copper oxide pyramids. The others have copper oxide sheets in between, which couple these pyramids. So what was argued at the beginning is that with rising distance in the unit cell between the single layers, with rising distance, one could increase the superconducting transition temperature. This seemed to be a scheme for the very beginning.
Okay, thank you.
Okay, so next person, please.
Thank you, Professor, for your lecture. I'm Anja from BRIN Indonesia and also student at Osaka University. Could you please share with us about how do you decide your multiple layer with various deposition?
How can I prepare? Is this right? We have different deposition methods, which is depending on which are used for different materials. Like say, electroplating is done for metals. For oxides, you would like to have either sputtering or E-beam evaporation. And this is a choice of different companies, how they do the different methods. It's not a must that you always need to do sputtering. You can also do E-beam evaporation, and you can also dip coating. It's a question of equipment people are willing to use. So there were for a long time there was an approach also in Germany where metal organic compounds were used by just evaporation, not by physical deposition methods. So it's depending on the company which type of layers they produce.
Thank you.
Next person, please.
So thank you very much for your wonderful presentation, Dr. Bird. I have two questions. So I'm particularly interested in the sheet type of the high temperature superconductor with different layers. So one thing I'm curious about is when you have a high current, what do you think about the thermal diffusion among those layers? Is it a problem or?
Superconductivity does not include heating, because if you have heating, then you need to have a resistance. And since the superconductivity is a state where you don't have any resistance, you also have no heating.
So the next question is, I'm curious about miniaturizing this superconductive materials. And I think one of the trending devices right now is quantum computing, which may be using superconductors with cooling. So are there any progress regarding the use of copper oxides in this particular field?
As far as I know, there's no attempt to use the copper oxides for these superconducting qubits. So far, whenever superconductivity is used, maybe you can also contribute to that. So far, it's done with a classical superconductor, with niobium and niobium compounds.
Thank you very much.
Yeah, because the time is already passed. So next is last question. So please.
Thank you very much, Professor. I am Rajdeep from Shimane University, Japan. So I wanted to ask you regarding the perovskite structure. So recently, many researchers are working on the optoelectronic parts like solar cell and absorber. So can you comment on that for the next generation solar cell?
Yeah, well, I didn't follow that very extensively, but I realized with very much interest that for the improvement of solar cells, perovskite type compounds, not conductors now, but optically absorbing compounds are used as at least as one additional layer on to improve the solar efficiency.
Thank you very much.
Okay. So now time is over, so I'd like to close the session. And finally, again, I acknowledge and thank Dr. BEDNORZ. Thank you very much.
Thank you very much, Dr. BEDNORZ and Dr. Ogino. Let's show our appreciation with a round of applause again.